that's doing the sweeping, and the total of all of that is not changing in time. That's a generalization, obviously, of the other one. Incidentally, the total of that is called the angular momentum, and this is called the law of conservation of angular momentum. Conservation just means that it doesn't change. Now, one of the consequences of this is, just to show what it's good for, imagine a lot of stars falling together to form a nebula, a galaxy. As they come closer in, if they were very far out and moving slowly, so there was a little bit of area being generated, but on very long arms, distances from the center, then if the thing falls in, the distances to the center are shorter now. If all the stars are now close in, then these radii are smaller, and in order to sweep out the same area, they have to go a lot faster. So as the things come in, they swirl around, and thus we can roughly understand the qualitative shape of the spiral nebulae. You can also understand in the same way, exactly the same way a skater spins when you start with the leg out, moving slowly, and as you pull the leg in, it spins faster, because when the leg is out, it's contributing, when it's moving slowly, a certain amount of area per second, and then when it comes in to get the same area, you have to go around faster. But I didn't prove it for the skater. The skater uses muscle force. Gravity is a different force, yet it's true for the skater. Now we have a problem. We can deduce often from one part of physics, like the law of gravitation, a principle, which turns out to be much more valid than the derivation. This doesn't happen in mathematics, that the theorems come out in places where they're not supposed to be. In other words, if we were to say that the postulates of physics were the law of gravitation, we could deduce the conservation of angular momentum, but only for gravitation. But we discover experimentally that the conservation of angular momentum is a much wider thing. Now, Newton had other postulates by which he could get the more general conservation law of angular momentum, but Newtonian laws were wrong. There's no forces, it's all a lot of baloney, the particles don't have orbits, and so on. Yet, the analog, the exact transformation of this principle about the areas, the conservation of angular momentum, is true with atomic motions in quantum mechanics, and is still, as far as we can tell today, exact. So we have these wide principles which sweep across all the different laws, and if one takes too seriously his derivations and feels that this is only valid because this is valid, you cannot understand the interconnections of the different branches of physics. Someday, when physics is complete, then maybe with this kind of argument, we know all the laws, then we could start with some axioms, and no doubt somebody will figure out a particular way of doing it. And then all the deduction will be made. But while we don't know all the laws, we can use some to make guesses at theorems which extend beyond the proof. So in order to understand the physics, one must always have a neat balance and contain in his head all of the various propositions and their interrelationships, because the laws often extend beyond the range of their deductions. This will only have no importance when all the laws are known. Another thing that's interesting in the relation of mathematics to physics is this, a very strange thing, that by mathematical arguments you can show that you can start from very many different apparent starting points and come to the same thing. That's pretty clear. If you have axioms, you can use some of the theorems. But actually, in the physical laws are so delicately constructed that the statements of them have such qualitatively different character that it's very interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out. But they sound completely different. 1, there's the forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion, rather, at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call a non-local quality. The force on this depends on where that one is over there. Now, you may not like the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says, different thing, completely different thing. that there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, and so on. And the number's changing, it changes rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in a direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. That's one statement. That's not enough yet, because I have to tell you now how to determine how the potential varies. I could say the potential varies as 1 over the distance from each object. But that's back to the action at a distance idea. However, the force is at a distance. But you can state the law in another way. And it says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one because it only tells what happens at one point in terms of what happens very close by. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space, because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy, in the qualitative ideas involved. You don't like action at a distance. You can get away without it. Now I'll show you one which is philosophically the exact opposite, in which there's no discussion at all about how the thing works its way from place to place, in which the whole thing is an overall statement, as goes as follows. When you have other particles around and you want to know how this one moves from one place to another, you do it as follows. You calculate a certain quantity you invent a possible motion that gets from one given place to some other place that you're interested in a given amount of time. Say it wants to go from here to here in an hour, and you want to know by what route it can get from there to there in an hour, by what curve. So what you do is you calculate a quantity guessing the curve. If you try this curve, you calculate a certain number for this quantity. I don't want to just say what the quantity is, but for those who have heard of these terms, this quantity on this route is the average of the difference between the kinetic and potential energy. Now, if you calculate this quantity for this route and for another route, you'll get, of course, different numbers for the answer. But there's one route which gives the least possible number for that, and that's the route that the particle takes. Now we're describing the actual motion, the ellipse, by saying something about the whole curve. We have lost the idea of causality, that the particle's here, it sees the pull, it moves to here, it goes. Instead of that, in some grand fashion, it smells all the curves around here, all the possibilities, and decides which one to take. This is an example of the wide range of beautiful ways of describing nature, and that when people talk that nature must have causality, well, you could talk about it this way. Nature must be stated in terms of a minimum principle. Well, you can talk about it this way. Nature must have a local field. You can do that, and so on. And the question is, which one is right? Now, if these various alternatives are mathematically not exactly equivalent, and if for certain ones there will be different consequences than for others, then that's perfectly all right then, because we have only to do the experiments to find out which way nature actually chooses to do it. Mostly people come along and they argue philosophically they like this one better than that one, but we have learned from much experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives. Now, in this particular case that I'm talking about here, these theories are exactly equivalent. The mathematical consequences in every one of the different formulations of the three formulations, Newton's laws, the local field method, and this minimum principle, give exactly the same consequences. What do we do then? You will read in all the books that we therefore cannot decide scientifically on one or the other. That's true. They're not equivalent. They are equivalent. Scientifically, it is impossible to make a decision, because there's no experimental way to distinguish if all the consequences are the same. Psychologically, they're very different in two ways. First, philosophically, you like them or don't like them. Training is the only thing you can do to beat that disease. Second, psychologically, they're different because they're completely unequivalent when you go to guess at a new law. As long as a physics is incomplete and we're trying to find out the other laws and to understand the other laws, then the different possible formulations give clues as to what might happen in other circumstances. And they become not equivalent in psychologically suggesting to us to guess as to what the laws might look like in a wider situation. For instance, Einstein noticed that the law of gravity, he said that he realized that signals couldn't propagate faster than the speed of light, for electricity. He guessed that it was a general principle, the same guessing game as taking this angular momentum and extending it from one case where you proved it to the rest of the universe. He guessed that it was true of everything, and he guessed that it would be true of gravitation. If the signals can't go any faster than the speed of light, it turns out that the method of describing the forces instantaneously is very poor. And in the Einstein generalization of gravitation, this method of describing physics is hopelessly inadequate and enormously complicated, whereas this one is neat and simple, and so is this one. So we haven't decided between those two yet. In fact, it turns out that the quantum mechanics says that, in exactly as I stated them, neither is right, but that the fact that a minimum principle exists turns out to be a consequence of the fact that on a small scale, particles obey quantum mechanics. And the fact is the best laws at present understood is really a combination of the two, in which we use minimum principles plus local laws. And the present day believes that the laws of physics have to have the local character and also the minimum principle. But we don't really know. So it's this way, that if you have a structure that's only partly accurate and something is going to fail, if you write it with just the right axioms, maybe only one axiom fails and the rest remains. You have to change one little thing. But if you write it with another set of axioms, they all collapse because they all lean on that. But we can't tell ahead of time, without some intuition and guesswork, as to which is the best way to write it until we find out the new situation. So we must therefore always keep all of the alternative ways of looking at the thing in our heads. So the physicists do Babylonian mathematics and pay little attention to the precise reasoning from fixed axioms. One of the amazing characteristics of nature is this variety of interpretational schemes which is possible. It turns out that it's only possible because the laws are just so unspecial and delicate. For instance, that the law is the inverse square is what permits it to become local. If it were the inverse cube, it couldn't be done this way. That the other end of the equation, that the force is related to the rate of change of the velocity, that's a consequence that permits this kind of a way of writing the laws, the minimum principle, because if, for instance, if the force were proportional to the rate of change of position instead of velocity, you couldn't write it in that way. If you try to modify the laws much, you find you can only write them in a very much fewer ways. I always find that mysterious, and I don't understand the reason. Why it is that the laws of physics always seem to be possible to be expressed in such a tremendous variety of ways. They seem to be able to get through several wickets at the same time. Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now, I explain that. If you state the axioms, you say, such and such is so, and such is so, and such is so, what then? Then the logic can be carried out without knowing what the such and such words mean. That is, if the statements about the axioms are true, are carefully formulated and complete enough, it is not necessary for the man who's doing the reasoning to have any knowledge of the meaning of these words, and he'll be able to deduce in the same language new conclusions. If I use the word triangle in one of the axioms, there'd be some statement about triangles in the conclusion, whereas the man who's doing the reasoning might not know what the triangle is. But then I can read his thing back and say, oh, a triangle, that's just a three-sided what have you, that's a so-and-so. And so I know this new fact. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all. I've already mentioned one other relationship that, of course, it's obvious how the mathematical reasonings which have been developed are of great power and use for physicists. That on the other hand, sometimes the physicist's reasoning is useful for mathematicians. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space. You know, you're in it and you measure distances and there are three numbers you need to tell where something is. You go breadth, width, and height, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in the special case. He's never interested in the general case. He's talking about something. He's not talking abstractly about anything. He knows what he's talking about. He wants to discuss the gravity law. He doesn't want the arbitrary force case. He wants the gravity law. And so there's a certain amount of reducing because the mathematicians have prepared these things for a wide range of problems, which is very useful. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4 dimensions. Now, another item that's interesting in this relationship is the question of how to do new physics. Is it important to have a feeling, a kind of intuition? Oh, I must mention one other item. When you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. Whereas a physicist who knows more or less how the answer is going to come out can sort of guess part way and go right along rather rapidly. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. Now, mathematicians can do what they want to do. One should not criticize them because they are not slaves to physics. It is not necessary that just because this will be useful to you, they have to do it that way. They can do what they will. It's their own job. And if you want something else, then you work it out yourself. The next point is the question of whether we should guess when we try to get a new law whether we should use the seat-of-the-pants feeling and philosophical principles. I don't like a minimum principle, or I do like a minimum principle, or I don't like action at a distance, or I do like action. The question is, to what extent models help? And it's a very interesting thing. Very often models help, and most physics teachers try to teach how to use these models and get a good physical feel for how things are going to work out. But the greatest discoveries, it always turns out, abstract away from the model. It never did any good. Maxwell's discovery of electrodynamics was first made with a lot of imaginary wheels and idlers and everything else in space. If you got rid of all the idlers and everything else in space, the thing was okay. Dirac discovered the correct laws of quantum mechanics for relativity quantum mechanics simply by guessing the equation. And the method of guessing the equation seems to be a pretty effective way of guessing new laws. This shows, again, that mathematics is a deep way of expressing nature, and attempts to express nature in philosophical principles or in seat-of-the-pants mechanical feelings is not an efficient way. I must say that there is possible, and I've often made the hypothesis, that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices. It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so I made the hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexity is from size. But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about this thing. To summarize, I would use the words of Jeans, who said that the great architect seems to be a mathematician. And for you who don't know mathematics, it's really quite difficult to get a real feeling across up to the beauty, or the deepest beauty of nature. C.P. Snow talked about two cultures. I really think that those two cultures are people who do and people who do not have had this, people who have had and people who have not had this experience of understanding mathematics well enough to appreciate nature once. It's too bad that it has to be mathematics, and that mathematics for some people is hard. When it's reputed, I don't know if it's true, that when one of the kings was trying to learn geometry from Euclid, he complained that it was difficult. And Euclid said that there's no royal road to geometry. And there's no royal road. It's not we cannot, as people who look at this thing as physicists, cannot convert this thing to any other language. You have, if you want to discuss nature, to learn about nature and to appreciate nature, it's necessary to find out the language that she speaks in. She offers her information only in one form. We are not so unhumble as to say, demand that she change before we pay any attention. It seems to me that it's like all the intellectual arguments that you can make would not in any way, or very, very little, will communicate to deaf ears what music, the experience of music really is. And all the intellectual arguments in the world will not convince those of the other culture. The philosophers who try to teach you by telling you qualitatively about this thing. Me, who's trying to describe it to you, but it's not getting across because it's impossible. We're talking to deaf ears. And it's perhaps that the horizons are limited, which permit such people to imagine that the center of the universe of interest is man. Thank you.